I want to take some time now to revisit an early topic, the periodic table. All right, so with this newfound knowledge of valence electrons, we want to take a look at what's going on the periodic table and kind of return to how the valence electrons are related. So if we look at hydrogen and lithium, 1s1 and then 1s2, 2s1 for lithium. And if we look at the periodic table, these are both in group 1a of the periodic table. They also both have just the single one valence electron. That is not accidental. Similarly, sulfur and selenium have 2 and 4, 2 and 4, for a total of 6 valence electrons. They are in group 6a of the periodic table. The arrangement of atoms in the periodic table is all based around electron configurations. In a given column of the periodic table, the atoms have the number of valence electrons equal to the group number. So group 1, all atoms have 1 valence electron. Group 6, they all have 6 valence electrons. When we go to the transition metals, it gets a little bit different. But if more importantly, we can focus on the fact that the Ds, 3D has 4, molybdenum, 4D has 4. These are both transition metals, and they are in the 4th group of the transition metals. Okay, so the arrangement of the atoms in the periodic table is based around the configurations of electrons. It's all about electrons. So, the underlying factor is all about electrons, and specifically those valence electrons, because we know that the periodic properties are based around chemical properties. A column of the periodic table all has similar chemical properties. Electrons govern chemical properties of atoms. So as a result, electrons underlie the organization of the periodic table. So if we take a look at want to plot out the periodic table, we can start to that organization, we can kind of start to chop it up. We can see that there is what's called an S block, the D block, the P block, and the F block. So these letters S, P, D, F correspond to the highest energy subshell of all atoms in those blocks. So any atom that's in, say, the D block, which we also call the transition metals, those atoms have their highest energy electron in a D subshell. Similarly, everything that's in the P block, all of those atoms have their highest energy electron in a P-type subshell. As a result, we can see that this affects the structure of the table, the SPD. We know that in an S subshell, you can put in 2 total electrons. So in the S block, there are 2 groups corresponding to putting the first electron and then the second electron. Then that S subshell is full and you have to go to the next level. So P can hold 6 total electrons. As a result, there are 6 groups in the P block of the periodic table. Similarly, D, you can put 10 total electrons in a D-type subshell. So there are 10 groups in the D block of the periodic table, right? Each atom has 1 more electron than the previous atom, right? And that means you have 1 more electron. They keep going into that D block. Similarly, you can guess that F is going to be 14 across. There are 14 groups in the F block because you can put a total of 14 electrons into an F-type subshell. So if we kind of want to put all this together and look at, say, an atom on the periodic table. So if we start with, say, period 2, because 1s is a little bit, it's only got 2 electrons. And if we start with period 2, we can see that that's going to be 2s, and we can see that we fill up those 2 electrons. You can put, as we kind of add up, going up numbers of electrons in an atom. If the atom, the highest energy electrons in the 2s, then there's 2s1, 2s2. That'd be full as we keep going up. We hit 2p. Then we need to put in 6 there. That's why this P block has 6 columns in it. Continues along, 3s, 3p. We're following that Aufbau ordering, 4s. Then with the Ds, it is shifted. That Aufbau has that weird shift. We hit the 3Ds, the 4Ps, and this continues. And so we can see that the arrangement of the periodic table is based around the electron configuration and is consistent. We can predict what the electron configuration of an atom is just based on where it is in the periodic table. And this just keeps going. 5s, 4d, the pattern of 5p. We're just following that Aufbau ordering, the ordering that we had previously that we used when we were coming up with electron configurations, because it's always going to follow this same pattern. After we get 6s, we do drop into the f's. We slot down here. The f's are shifted off by 2, just like the d's were shifted back. The f's are shifted by 2, 4f, 5d, 6p, 6s, 5f, 6d, 7p. So we just go across. There's all sorts of stuff. And so we can then fill basically our orbitals as we would fill them up. And this is why we said Agnessen in the last set of slides was at 7p. That's in the bottom right here. Boop, boop, boop. 7p is then going to be its highest subshell. So that's why we don't need anything else for the current atoms on the periodic table. If you made a bigger atom, you would then have to go up to the next highest subshell. So we can also see that this is why we have this tiered nature of the periodic table. The D's kind of slot in, they're shifted back on those S's, the F's are slotted in as well. That tiered nature just comes from the pattern of the subshell ordering, right? You have the 1s, 2s, 2p, but then instead of 3s, 3p, 3d, those S's pop back in, so the 3Ds have to be shifted back. And so we have this nature of kind of coming in, and there we could have more. There would be another rung down here of the G's. Okay, so why this is useful is it lets us, say, interpret the electronic structure, electron configuration, just based on where an atom is in the periodic table. So for example, oxygen. Oxygen has the electron configuration 1s2, 2s2, 2p4. Okay. If we look, we can see that it's in period 2, right? And so oxygen's in period 2. That's why there's a 2 in the highest energy subshell. Then we can see it's in the p block, which means that the highest energy subshell is p-type. Within the p block, it is in the 4th group, right? 1, 2, 3, 4. It's in 6 across, but that is the whole period. We're just talking about within the p block, it's in the 4th group. That's why it has a 4 right there, because there are 4 electrons. Boron has 1, the B, carbon C has 2, nitrogen N has 3, O has 4, F has 5, right? So they are just adding up those electrons that are in this particular p subshell. We can also use it, then to kind of figure out, say I want to know the electron configuration of iron. Well, what I can do is, we counted up doing Aufbau, we would start, well, 1s2, 2s2. And so we can kind of go through that process, but we can also start at the other end. Based on where iron is in the periodic table, we can predict what the highest energy subshell is. We know that it's in the D block, and we know it's in the 6th group of the D block. SC starts at 1. We can just count across 1, 2, 3, 4, 5, 6. So we know right away that the electron configuration ends with D6. Anything that's in the same column as iron ends with D6 as its electron in the electron configuration. So then the question is, what number goes in front of that D? And that number is going to come from the period that it's in. So iron is in the 4th period. So for S and Ps, when S and P type subshells, whatever period is, that's the shell you're in. But Ds are shifted by 1. So we get period minus 1 for N. That means it's 3D6. So what that tells us is that the electron configuration ends with 3D6. Everything that's below 3D6 is guaranteed to be full. So we don't need to think about any of that. We just know 1s, 2s, 2p, we can just follow the Aufbau ordering and put as many electrons as possible into those subshells. Then 3D has 6 electrons inside of it. And that is guaranteed to be iron. So we want to look at some examples. What is the highest occupied subshell on each of the following atoms, and how many valence electrons does it have? So I got GE, BA, ZN, and KR. Okay. So if I take a look here, when I'm going through this, I want to start by asking, where is the atom on the periodic table? That is always going to be my first question. because the location periodic table arrangement is based around electron configuration. So if I ever want to know information about that, it's always just going to come from where is it in the periodic table. Then I can kind of give information on what block is it in, what period is it in. You know, that S&P blocks have some interpretations based on end to period. And then, you know, valence electrons are based around what group it's in. So, all right, so first is germanium. Germanium is right here on the periodic table. And so the question we want to ask is, what block is it in? Well, the block right here is P. So we know right away that we are in the P block. Okay? And because we're in the P block, we can just come right over here and see we're in period 4. So we know right away that the highest subshell is 4P. Okay? Germanium is guaranteed to have its highest subshell be 4P. We could also predict within the P block, we are at 1, 2. So it's going to end with 4P2. There's 2 electrons in that 4P subshell. If I want to know total valence electrons, I just come, look right there. I'm in group 4A, 4 valence electrons. You can write out an electron configuration for germanium if you want to. You don't need to though. You can just figure out that it's in the 4th group, 4 valence electrons. Barium, Ba. Barium is right here on the periodic table. And the first thing we want to know is what block is it in? It is in the S block. So those 2 columns are the S block. Group 1A and 2A are in the S block. For S block, we just need to look at the period. It's in period 6. Sorry, it's a little crossed out. So the highest, it's in the S block in period 6. So 6S subshell is going to be the highest. Similarly then, we can just take right here, look at the group. We are in group 2A, 2 valence electrons. Zinc. Zinc is right here. So zinc, Zn, that is in, oopsies, that is in the D block. D block is, we already have a name for it. It's called the transition metals. So D block is just another way to say the transition metals. So we know anything that's in there is going to have its highest subshell be D. Zinc we can see is in period 4. The D's are shifted by a little bit. With S and P, you can just take that number. With a D, you need a -1, so -1 to it. So that's why 4 minus 1 gives me 3D. So the highest energy subshell on zinc is 3D. That's going to be true for anything that's in the 4th period in the D. So starting with SC scandium and going all the way across to zinc, you can put a lot of electrons in there. So now for determining the valence electrons. Previously, we just used those group numbers that had the A's in them. You'll note in this periodic table, there is this other number that's in parentheses. Sorry, I've kind of covered it up now. And it's a 12 under zinc. In zinc, there are 12 valence electrons. So we don't want to use, when we're determining it, this B value. We want to use that 12 that's in there in parentheses. So for example, cobalt is 9. There's 9 valence electrons in a cobalt atom. Whenever we're looking at a transition metal, we always want to use that number that's in parentheses, not the number with the letter next to it. For S and P blocks, we use the letter that's next to it. Okay, Kr is krypton, right there. And so krypton, we want to think about what block it's in. Well, the block is going to be this long trace. That is the P block. Okay, so krypton is in the P block of the periodic table. So we know it's going to have P. We then want to look at, for P, just what the period is. It's 4. And so that means krypton is 4P for its highest energy subshell. So that last electron that was put into 4P. And then the valence electrons, it's in group 8A, 8 valence electrons. So Kr krypton has 8 valence electrons. Participation 622, question 3. How many valence electrons do the following have? Si, Se, Ne, alkali metals, and halogens. This is the third question on participation 622, due Monday, June 22nd at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, how many valence electrons do the following have? Si, Se, Ne, alkali metals, and halogens. Okay, there's another participation question. 622, only one video left in the set. See if we can find any more participation questions than that one. I'll see you there.